this morning. Nigel Hitchin will tell us about the Dirac operator for
Okay, well, thanks very much. It's a great pleasure to be here speaking at Blaine's 70th birthday. I chose to speak on the Dirac operator for two reasons, I guess. One is in homage to the book of Blaine and Marie-Louise, on spin geometry, which is surely the standard text on the Dirac operator. Certainly, when any of my students ask me about the Dirac operator, I just direct them towards the book. The second reason is that I first met Blaine 40 years ago at the Institute in Princeton, and I'd just written my thesis on the Dirac equation, and I remember Blaine was just getting ready to go back to Berkeley. He was going to drive across country, and I asked him, I said, well, this must be a very boring journey, and he said, but I'm going to take Hitchin's thesis. So I was very pleased about that. How he managed to drive and read the thesis at the same time, I don't know. Anyway, so this is about the Dirac operator, but maybe not quite as we know it. So let me set it up for you. So I'm really interested, have been for many years now, in this set of equations on a Riemann surface. So you have say a compact Riemann surface, you have a holomorphic vector bundle E over it, with a Hermitian metric, and you have an auxiliary field called a Higgs field. So this is a twisted endomorphism. It's a section of the holomorphic section of the endomorphism bundle twisted by the canonical bundle. And the curve, so when we have a Hermitian metric, of course, and a holomorphic structure, then we have a connection, a unitary connection. And the curvature of this connection couples to the Higgs field by means of these equations. In fact, the history of these equations really, I got seriously interested in these when I visited Stony Brook in 1983, 84, and I got talking to Martin Rocek about hyperkähler quotients, and the moduli space of these turns out to be a hyperkähler manifold as a consequence of an application of the hyperkähler quotient construction. So maybe it's doubly appropriate that I talk about this here. So what are these equations? Well, and what have they got to do with the Dirac operator? Well, if you actually look at them locally, and this is the way I got interested in them. Okay. First of all, it was in 1983, 84 that I first started writing down these equations, but quite recently, because of another talk I had to give, I tried to find out where they'd appeared before. And as usual, it's the physicists who found these equations first. So this is a 1977 paper. And, the notation is different, but as you see, it was dismissed in this paper. The model is not interesting because the action is always zero. So the point about this is that Lohr was considering these equations on R2 and not on the Riemann surface. And indeed, if you look at solutions to these equations, where there's the action, the L2 action, the norm squared of the curvature plus these derivatives of the Higgs fields, whether that's finite, then there aren't any interesting examples. But the great thing about this is that the equations can be made to be conformally invariant and then put onto a Riemann surface, in particular a compact Riemann surface. So in fact, why was a physicist in 1977 interested in this, and why did he discuss this in the context of instantons? And this is because actually locally, so in R2, these actually are special cases of the anti-self-dual Yang-Mills equations. So if you have a solution to anti-self-dual Yang-Mills, which is invariant under translation in the last two directions, then the covariant derivatives, so these, you have phi 1 and phi 2, these are now skew-adjoint endomorphisms. These you can think of these, if you like, as connection forms, but which are invariant under translation. And then the equations come down to these. So these are the three equations for the anti-self-duality equations for such a connection. And the first one is when you wrap it up in this other way. The first one is this real equation like this. You put the phi 1 and the phi 2 together into a complex object, And then these are basically the Cauchy-Riemann equations, which is saying that phi is holomorphic. So it's that reduction from R4 to R2 which gives you these equations, and then you observe that they make far more sense because F is a 2 form. If phi is a 1 form, then this makes sense, equating a 2 form to a 1 form, and so that's why you kind of liberate these phi 1s from being Higgs fields, just scalars, to being forms. Anyway, so they are, locally, these equations are special cases of the anti-self-dual Yang-Mills equations. And the challenge, is really to solve these equations. Like in 1977, we solved the construction of instantons, and we looked at finite action solutions to the self-dual Yang-Mills equations in R4. You could reduce them to matrices, nonlinear equations for matrices. So I put this as a challenge rather than a problem, because it's not a program which I expect to be realized, not even before Blaine's 80th birthday. And why? Because just look at a couple of examples. What would it mean? So here's two special cases. So if that Higgs field is 0, then this is the equation for a flat unitary connection. So as we know, there's a theorem of Narasimhan and Seshadri, which says that if you start with a stable holomorphic vector bundle on a Riemann surface, then there's a unique flat unitary connection on it. So what this would say would be, can we go from a holomorphic description of a stable bundle through some process? Can we describe the actual flat unitary connection on this bundle by some systematic process? Of course, we have an existence theorem, but we don't have a systematic way of writing down the solution in terms of some succession of definable processes. The other extreme is this. If you take the vector bundle to be the direct sum here of the square root of the canonical bundle plus its dual, then there's a canonical Higgs field. So you see what's happening here? So U here is a local section of k to the half, and it's shifted over here, but phi is mapping E to E tensor canonical bundle, and k to the minus a half tensor the canonical bundle is k to the half. So this is canonically determined. And if you solve the Higgs bundle equations for this is what's called a stable Higgs bundle. If you solve the equations, then actually they correspond to finding the hyperbolic metric on a Riemann surface. The equations, for various reasons, the metric respects this direct sum decomposition. So it's a Hermitian metric on the canonical bundle, or its square root, and that turns out to be a hyperbolic metric. So to actually solve these equations in some other form, in some explicit or quasi-explicit form, would mean going, let's say, from the equation of an algebraic curve through some systematic process to finding the hyperbolic metric on that curve. And that's really a long shot, which is why I call it a challenge, but there's no harm in trying to see what you can do. And that's really what I want to talk about today. It's a problem that I've had in my head for many, many years. I've tried it with a few students. I have a student at the moment, Jakob Blavand, who's working on certain aspects of it. And it all revolves around properties of the Dirac equation. So let's see, first of all, why did the Dirac operator play a role in the construction of instantons? So this is going back to 1977. And we're looking at an anti-self-dual connection on a bundle, vector bundle E, let's say, over the 4 sphere. Then the Dirac operator, of course, goes from spinors with plus chirality with minus chirality. And we have a Weizenbach formula, the one that Jean-Pierre Bourguignon spoke about, the Lichnerowitz formula, or nowadays it's always called, not always, sometimes called the Schrödinger-Lichnerowitz formula. So usually, we got the quarter of the scalar curvature, but usually there's a term involving the curvature of this auxiliary bundle E. But if E is anti-self-dual, then the curvature acts trivially on the self-dual 2 forms, and so we just get the Weizenbach formula for the ordinary Dirac operator, and of course the force sphere has positive scalar curvature, so the kernel of this D operator is equal to 0. And then you apply the index theorem, and you find that the dimension of the kernel of D star is k, where so k is some integer. It's basically the second Chern class of this bundle E. But that's on the force sphere, and that's the way we would normally do Riemannian geometry. But you can do it on R4 if you look at L2 solutions. And so here there is another way of writing the Dirac operator. So we're now on flat R4. We have the same behavior, and in a sense, because the anti-self-dual equations are conformally invariant, we can go to R4. And then it's kind of convenient to write this operator D as a quaternionic operator. So we trivialize the spin bundle. And so this is, if we replace I, J, and K by the Pauli spin matrices, then it looks more like a Dirac operator. But you can say that the anti-self-dual Yang-Mills equations are equivalent to saying that D star D is a real operator. So that's just looking at the equating to 0 the coefficients of I, J, and K when you write down D star D. So the anti-self-duality condition is equivalent to saying that this operator D star D is real. And what does it mean if you look at it? What it means is that it's actually not only real but positive. So here we're on R4, so that scalar curvature term disappears. But if we're looking at L2 solutions, that's the L2 solutions which extend to the force sphere anyway because of conformal invariance, then we have a k-dimensional space of such things. And then you define matrices in this way. So for each coordinate xi, 1, 2, 3, 4, you define a matrix by multiplying this L2 spinner by xi, taking the interior product with the psi, L2 interior product, and this gives you an action, a k by k matrix, well, 4 k by k matrices. So these are basically what goes into the ADHM construction. There's another set of matrices which comes from behavior at infinity. But the idea is that in order to get this transform from a solution to the anti-self-duality equations over to this algebraic data, what you have to do is first of all solve a Dirac equation and then do some manipulation and you get the solution. So this sort of approach only became apparent when something similar called the norm transform was applied to monopoles. Well, given that this is what you do for instantons, so the obvious thing to say is if you want to do something for the Higgs bundle equations, which are dimensional reductions of the instanton equations, the obvious thing to do is to define an analog of this Dirac equation. So what is the Dirac operator for Higgs bundles? Now, normally speaking, and I don't know which chapter of the book it's in, but you usually think of spinners on a Riemann surface as taking the square root of the canonical bundle, just that I did, and looking at the d bar operator on that. This is a slightly different Dirac operator. So what we're going to do is to say, well, let's look at the Dirac operator that we had in R4 and to just see what it is under dimensional reduction. So it's this d star operator here, but now we replace the covariant derivatives in the last two entries with the Higgs field. So what you get there is a differential operator. So I call it the Dirac operator because it's basically the R2 invariant. It's the dimensional reduction of the Dirac operator which worked for the instantons. And if you write it down in R2 at least, then you can write it this way. So A is the connection, which has covariant derivatives, nabla 1, nabla 2. And then you have the 0, 1 part and the 1, 0 part of this connection. So what does it look like globally on a Riemann surface? So it's really acting this way. So you take your bundle, your holomorphic vector bundle, and you tensor it with k, so this is what it looks like. It's a map from sections of E tensor k plus E tensor k bar to sections of E tensor k bar twice. So it's going from one forms to two forms, basically. And so the idea is that somehow this should be the key to any transform which is analogous to the way that these ADHM equations arose. Now, if you look at it again in R2, I mean, you look at this rather formally, you see that d star d again looks like a positive operator, so the kernel of d is equal to 0. And now the index theorem on a compact Riemann surface tells you that the dimension of the kernel of d star is this dimension has rank, there's dimension 2g minus 2 times the rank of A. So that's just the index theorem. Well, the index theorem is obvious. I mean, the index is, you can put phi equal to 0, and then it's just the sum of indices of a d and a d bar operator. Okay, so we have the same kind of feature. We have that the kernel of D is 0, and so then we look at its co-kernel, which is the kernel of D star, which has this particular rank when you have a solution to these equations. So another point to notice is that so if you now have a solution to the equations, it's given by a pair of sections, one of EK and one of EK bar. Then there's an inner product, there's an L2 inner product. You use the Hermitian inner product on the vector bundle. And then because these are forms, then you multiply two forms, or you take a form, wedge its star, and integrate that, and that gives you a natural inner product. So this depends only on the conformal structure of sigma. You don't have to choose a metric. So you have an inner product a natural inner product on the kernel of D star. Natural, it depends on the solution to the Higgs bundle equations. It depends on the Hermitian metric on E, but not on any Hermitian metric on the Riemann surface. So if you want to see the simplest example is where you take E to be a trivial line bundle, and phi then is a holomorphic differential, so let's just take dz, and then what do these equations say? They come down to this. So you're basically looking at eigenfunctions of the Laplacian on psi1, so on R2. So locally, this is described by solutions to an equation like this. If you really want to You see, if you really want to look at the Dirac operator for the trivial line bundle, then locally this is really what happens, except at the points where the holomorphic differential vanishes. So if the holomorphic differential is non-vanishing in some region, then you can, small enough region, you can choose holomorphic coordinates such that it actually looks like dz, and then local solutions are given by solutions to this equation. And you could expand this, if you like, in a Fourier series where the coefficients will be Bessel functions now instead of r to the n. So that's the sort of equation that we're dealing with. Okay, so now what you have to do is to try and decide what to transform it into. So far I've just got a single Dirac operator, and I've got a vector space out of it. So what you can do is to produce a family of such vector spaces. In fact, a vector bundle over an auxiliary space. So this is I've called it Fourier transform, but it's really, a norm Fourier transform, really. The ideas in this gauge theoretic context really belong to norm. And so here are the various places where this idea has appeared. I'll talk about how they appear a little later. So Johannes Bonsdorf was one of my students some years ago, and he's since left mathematics, but he wrote a couple of papers in an algebraic geometric context. Marcos Jardim, he was also partly my student, And he was looking at a different problem, but it actually involved the same kind of ideas. But I'll mention the link a little later on. Okay, so what you do is this. So you take a given Higgs bundle, so we're going to fix E and phi, then we're going to modify it by an abelian Higgs bundle. So that means that we're going to, first of all, tensor the holomorphic vector bundle E by a flat unitary line bundle. So this is a holomorphic line bundle with its flat unitary connection. And then we're going to add on to the Higgs field the multiple of the identity. So we have a holomorphic one form times the identity. So what are the parameters here? Well, the flat line bundle lies in the Jacobian of the Riemann surface, and theta lies in this g-dimensional space of holomorphic differentials. So basically all we've done is to say we have this Higgs bundle and we're tensoring with a U1 Higgs bundle. What is a U1 Higgs bundle? Well, it's that equation F plus phi star equals 0. U1 is abelian, so the equation is F equals 0, and phi is holomorphic. So that's why we've got a flat line bundle and a holomorphic one form. So you do this, and then you look at the kernel of this operator, this Dirac operator, and it defines a vector bundle over this. So maybe you choose a Poincare bundle, and it gives you a vector bundle over what I write here as the cotangent bundle of the Jacobian. So Jacobian is, of course, a flat torus, so it has a trivial tangent bundle. This is naturally the cotangent space. And so what we get is a family of vector bundles, a family of vector spaces, a holomorphic vector bundle over this cotangent bundle here. And as I said before, when you have a solution to the Higgs bundle equations on E, then it defines a Hermitian metric on E, and by the integration, this L2 in a product defines your Hermitian metric on this vector bundle, and so we have a connection, an L2 connection defined by the holomorphic structure and the Hermitian structure on this vector bundle over here. So it's a rather larger vector bundle. You know, if my original one, say E was rank 2, then it's rank 4G minus 4, this vector bundle over here. Okay, but when you have a holomorphic vector bundle and a Hermitian metric on it, then you get a connection, but this connection has a very special property that it's actually hyperholomorphic. So what does that mean? Well, so what we've got on this space of parameters is actually a hyperkähler manifold. It's a flat hyperkähler manifold. So I have the Jacobian has a natural Kähler structure coming from the theta divisor, coming from the structure of the Riemann surface. And so it's got a flat Riemannian metric, and now we're just taking the cotangent bundle of it. This has a flat hyperkähler structure. So to be hyperholomorphic is to say that it's holomorphic with what it says is that it's, first of all, that its curvature is of type 1,1 with respect to the complex structures I, J, and K. What are they in this particular case? Well, there are basically I and minus I are the only ones which are different from anything else. So that is the complex structure of the product, J cross CG, and the other ones, in particular J and K, the complex structure is equivalent to this product of 2G copies of C star. I mean, the reason for that will appear in a minute. So the complex structures are different. This one, of course, has compact subvarieties, namely the Jacobian and all the curves and higher dimensional special varieties inside it. This one has, of course, no holomorphic compact subvarieties. Okay, so this is what hyperholomorphic means, that the curvature is of type 1,1 with respect to I, J, and K. And what that means in particular is that it has a holomorphic structure with respect to I, J, and K as well. So why is it hyperholomorphic? Well, I'll give you two ideas of the reason. One is actually going back to the ADHM construction, which is, of course, a long time ago. But anyway, the idea there is that you have matrices, A and B, quaternionic matrices, which depend linearly on a quaternion Q, and they satisfy the condition that D star D is equal to real, is real. And then basically you look at the orthogonal projection onto the co-kernel of this as Q varies, and then it's a simple calculation using second fundamental form to see that means that the curvature of that is some linear combination of the coefficients of dq, dq bar, which are basically the anti-self-dual forms. So formally speaking, what we've got is the same thing here, that our Dirac operator now, when we do this modification by tensoring with L, so by tensoring with L, I'm representing that here by adding on, let's say, a harmonic 0-1 form here, then this is like D star plus Q, where Q now lives in this 2G dimensional, anyway, this 4G real dimensional quaternionic space, namely the space of A's and theta's. So it's the same, formally speaking, it's the same type of reason as why the ADHM matrices give you an anti-self-dual connection, because the condition here is that D star Q plus times D plus Q bar is actually real. But maybe there's a more explicit way of saying this, which is to look at what does it mean to say, what is the holomorphic structure of this kernel of D star if we look at the different complex structures I, J, and K. So with respect to the complex structure I, then what you've got is, so you're basically looking at this D star operator is really is related to the Hodge theory of the D bar plus phi operator, thought of as the total differential of a double complex. Now, we're only on a Riemann surface, so actually there aren't many terms here. P is either 0 or 1. But this is the so what we've got here is what is this? The total differential of a double complex. This is basically the hypercohomology. We're looking at the cohomology of this, but the D star is really the Hodge theory. It's D bar plus or minus phi plus D bar plus or minus phi star. And so we know by Hodge theory that the kernel of D star is actually isomorphic to this hypercohomology of this double complex here. So that has a holomorphic structure with respect to the complex structure I. If I look at the complex structure J, then we understand this as in terms of the Higgs bundle by saying that those Higgs bundle equations tell us that this object here is a flat connection. It's a flat GLNC connection. So this is the covariant derivative of a unitary connection, but this is now self-adjoint rather than skew-adjoint. So put together, it gives a flat GLNC connection. And then what you're looking at, this Dirac operator, becomes interpreted as the Hodge operator, the D plus D star operator, just for the, if you like, the de Rham cohomology, the flat de Rham cohomology. If you like, think of E with this flat connection as being a local system, and then we just have the H1 of the usual de Rham cohomology with respect to this this flat bundle. So these are two very different interpretations of the kernel of D star, and in fact, if you put it all in the right context, it's equivalent to say to describing this as a hyperholomorphic bundle. So how does that affect the Fourier transform? So that was so actually I haven't said that yet. All I've done is describe for a fixed Higgs bundle what this cohomology is. But now, if I now have a family which is parametrized by my cotangent bundle of the Jacobian, then I'm really looking at, so in the complex structure I, on that flat hyperkähler manifold, I'm actually getting the, maybe it's better to write it this way, it's the hypercohomology of this very short complex of sheaves. So I've got the Higgs field, holomorphic Higgs field going from here to here, then I'm adding on theta times, just theta times the identity. And in the complex structure J, I think of my line bundle together with theta, I think of harmonic 0-1 form and a holomorphic 1-0 form, as put those together, and that defines me a flat C star line bundle. And then I'm looking at tensoring this, the given flat structure on E by this flat line bundle here, and varying L over the over this space, the space of flat line bundles. So this is the product of 2G copies of C star that I was talking about before. So the Fourier transform gives you a holomorphic bundle with respect to all of these complex structures. And one way of looking at this, in fact, probably the best way of looking at it is to put all these complex structures together into a twistor space, and to say that then actually a hyperholomorphic bundle is totally equivalent to a holomorphic bundle on the twistor space of this flat hyperkähler manifold. So maybe I should say just a little bit about what the twistor space is. It's pretty basic. So you have this class here given by the theta divisor. So this is in H11 of the Jacobian. So if I think of that as a class in H1 of the sheaf of holomorphic 1 forms, then that defines me an extension, a vector bundle, so H1 of homomorphisms from this to this. That defines me a rank G+1 vector bundle. Then if I take the projective bundle of this, then there's a distinguished hyperplane bundle, namely P of T star. What I get that way is an affine bundle over the Jacobian. What it is this. So this is the complex structure J. This is a flat holomorphic line bundle. I can associate to it the holomorphic structure, which is J. If I fix the holomorphic structure on a vector bundle, then any two flat connections differ by a holomorphic differential, and so that's an affine space. So this is basically, this flat affine, this affine bundle is actually just as a complex manifold, it's C star to the 2G, but it's represented this way as an affine bundle over J. So now I can do that for actually any multiple of theta. Of course, it doesn't really change the structure of this, it just changes the extension class. So if I let zeta now if I let zeta be a parameter here, zeta in C, that gives me a bundle. I get these affine bundles over J cross C. But then when zeta equals 0, the extension is trivial, and then what I get is basically the product. So this is just a universal deformation of the cotangent bundle into what's called the twisted cotangent bundle. So what you do to produce the twistor space is this: that you look at, you have a flat connection. You look at the space of flat connections here. It has this projection to the Jacobian, which is basically taking the holomorphic structure of nabla 0-1, the holomorphic structure of the flat connection, defined by the 0-1 part. But then you could take the 1-0 part, which gives you a holomorphic structure on the Jacobian of the curve with the opposite complex structure. And then you identify these two families over the intersection, where zeta is identified with zeta inverse. So you're basically patching together two deformations of the product into affine bundles. Well, there are other ways of saying that, but it's a flat twistor space. You could also think of it as the quotient of 2G copies of the line bundle O1 modulo a lattice acting. So what is the conclusion of all this? That I start with a Higgs bundle, and what is its Fourier transform? So the Fourier transform is this rank RKE 2G minus 2 bundle E hat on this with a hyperholomorphic connection, and that's equivalent to a holomorphic bundle on this twistor space. So, so what are the questions? So these questions arise by analogy with the other situations where this transform actually works. So for monopoles and instantons, you can actually invert. So, but first you can ask these lower level questions. So does this holomorphic vector bundle actually encode the information of the Higgs bundle and its metric? So what have we done? We've made the situation more complicated by, we've gone to this big hyperkähler manifold, and we have this big vector bundle over it. On the other hand, the hyperkähler manifold is flat, and all we have to do is find on the twistor space, we need to find a holomorphic bundle. So it's abelianized the situation. So we started with something small. We started with the Riemann surface, let's say a rank 2 bundle, but unwrapping the Riemann surface into coordinate patches is something which you can't do. This is a global way of going from that highly nonlinear but kind of small situation to something which is more linear, more understandable, hopefully. So this, I mean, I believe that this actually can be answered. I think that there's some injectivity which one ought to be able to answer in this way. More difficult is what is the inverse transform. You know, suppose we have this holomorphic vector bundle on this twistor space. How do we go back? The problem there is basically that everything is non-compact on the right-hand side, and so you need to have some growth conditions, at the very least, to be able to try and do an inverse transform. And the final one is, you know, suppose we can find the transform of the canonical Higgs bundle? In other words, is there some object on the right-hand side, some natural holomorphic vector bundle on this twistor space, which is in a different formalism, the hyperbolic metric? Can we actually characterize it, even if we can't explicitly go backwards? Well, I don't know the answer to any of these questions, but there is evidence for, at least for number one. So let me, so there aren't any theorems that I'm going to talk about, but let me actually try and describe what we know about this situation. And mainly this will be about this complex structure I. So let me recall two basic facts about hypercohomology, or one basic fact. So we're looking at the hypercohomology of this short sequence of sheaves. Then that hypercohomology appears in this situation in two exact sequences. So there are two spectral sequences associated with a double complex. One of them tells you that the thing that we're after sits inside a sequence like this. And so again, so when we put in the twisting by the line bundle L and the modification of the Higgs field, then this will be a picture, there'll be a bundle with this kind of structure. And the other is that you can look at the cohomology sheaves of this, and that's much simpler because this is, if f phi at least is non-zero, then this, or let's suppose also that it's maybe not nilpotent, then this H1 is basically, you're looking at the sections of the co-kernel of this. So if the determinant of phi, which is a section of the nth power of the canonical bundle, if that is not identically zero, then this cohomology you can think of as being supported on the zeros of the differential, this n-fold differential, which is given by the determinant of this. So this is a more concrete way of kind of discussing this, but this can also be useful. So what have we got here? So okay, so this is the first thing. So this is what one of the things which Bonsdorff achieved. If you look at it from the point of view of this hypercohomology, then so we're looking at this thing here. So theta lies inside the cotangent space of this Jacobian. So the question is, what happens as you go to infinity? Well, in this realization, you can easily see what's going to happen, because you can put in an x0 against phi and an x1 against theta, and you can kind of projectivize this. And you see that there is actually a natural extension of this hypercohomology sheaf to the compactification, the naive compactification of the cotangent bundle. You just take the projective bundle of the cotangent bundle plus the trivial bundle. What it is that's putting x0 equal to 0, so it's just the hypercohomology of multiplying this by the holomorphic one form theta. So that is, if you like, the H1 of that is supported on the zeros of the holomorphic differential theta. So that's a good feature, because we've now gone from a non-compact complex manifold to a compact one. And what he did was also work out now the Chern character of this transform bundle, and also some cohomology groups. So this way, using this compactification, you can get quite a lot of information about it. But that's just information about E hat as a holomorphic bundle. So you do get something. So here's an example. So suppose we start with a stable bundle. That's where the Higgs field is 0. Then if the bundle is stable, then stability means that there are no holomorphic sections. And we have fixed dimensions then by Riemann-Roch for H1. So what you do is, so if you choose a Poincare bundle, then you have a Picard bundle. So if you like, you look at this space here, whose dimension is this, and let L vary over J, and that gives you this so-called Picard bundle over J. What you need is the direct image, first direct image of a twist of this Poincare bundle. So this is a recognizable bundle over J. It's the sort of thing which has been studied perhaps, well, maybe not with a stable vector bundle, but been studied in different contexts before. And here, so here we have that this hypercohomology that we're looking at sits between these two. It's an extension of these two vector spaces of this particular rank. So what that means is that the Fourier transform is actually an extension of of a Picard bundle on J, a pullback of a Picard bundle on J, and one on J, twisted with O1. So O1 is the line bundle on PG. And then, okay, so then actually it turns out that this is a non-trivial, this is a trivial extension. So actually this Fourier transform is basically, it's rather simple in this case. It's the pullback of one of these Picard bundles plus the pullback of the other twisted with O1. So there are situations where you can actually see what this holomorphic structure is on this compactified, this J cross PG. The other thing that Bonsdorff did was actually to show that so he set the whole thing up in a very algebraic formalism, and as a general Fourier-Mukai transform, and then showed that this Fourier-Mukai transform gave an equivalence of derived categories, which meant that you could, first of all, you could recover. So if we started with a short complex, just this one here. So this is an object in the derived category on the left-hand side. It gave us a vector bundle on the right-hand side, and because of this equivalence, you get something that is that's uniquely determined up to derived equivalence by something on the left-hand side. But he shows that actually that's enough to recover this as a holomorphic object. So this is a kind of partial answer to my first question, which was, does this hyperholomorphic connection, does it capture the information of the original Higgs bundle? So it's, in a way it does. The trouble is that what we've used is an extension to this compactification. So what's not clear is whether the behavior of the hyperholomorphic connection on the Jacobian times CG is what gives us this extension. So the extension is because we know what it is here. We know we can describe it by hypercohomology, but it's not clear that that's not quite clear that that's determined by the connection itself. So that raises the question about what is the asymptotic behavior of the connection as you go off to infinity. The holomorphic structure extends, fine, but what happens to the connection? The connection is not going to extend, but how does it blow up? And that's really the topic that we need to learn more about. Because if we can see how to extend, to do this holomorphic extension, purely in terms of the asymptotic geometry of the connection, then we can at least say that the connection contains all the information about the original Higgs bundle. So this is the question. We have a connection on a bundle over this. What is its asymptotic behavior as you go off to infinity? And why does the holomorphic structure extend? Well, I don't know the answers to all these, but that we can make a start. And in a way, this goes back to Jardin's problem. This is his thesis problem. So this is the opposite point of view. So he began as Simon Donaldson's student, and the problem was to find doubly periodic instantons, and that means to find solutions to the anti-self-dual Yang-Mills equations on the product of a 2 torus and R2, which had finite action. And what he showed was that, if you like, he inverted what I'm talking about, but of course, this is the Jacobian of a torus, the dual torus, but there aren't any interesting Higgs bundles, there aren't any interesting non-singular Higgs bundles on the torus, and that's reflected in the fact that these boundary conditions tell you that you're going to get a Higgs bundle with 2 singularities. So it's a kind of model, but it says that, in a sense, when you put singularities in, then here is some asymptotic behavior of the transform connection. So now we're in 4 dimensions, so hyperholomorphic is the same as anti-self-dual, in fact. And so life was simple for him because it was simply the L2 condition on the curvature. And in fact, what he did in order to prove the injectivity was to show that the holomorphic structure extended to T2 across P1, and then he could begin to use algebraic geometry as well. So that was a kind of model for what Bondorf was doing, but it doesn't really help very much when we've got a Riemann surface of higher genus, and we've got a bigger hyperkähler manifold, the product of the Jacobian and CG. So we want to understand something about the asymptotic behavior as t goes to infinity of solutions to this Dirac operator here. So this is going off to infinity in this space here. Okay, so we're not bothered about tensoring with the line bundle now because that takes place in a compact variety, the Jacobian. So here you can apply basically the same sort of techniques that occur in Witten's proof of the Morse inequalities. So Witten he looked at the exterior derivative conjugated by e to the f, where f was a Morse function, and then looked at, or e to the tf, and then looked at the behavior as t went to infinity. So here our t is kind of built into the operator. So if we take this Dirac operator here, and we look at the Weizenbach formula, then there are terms, I won't spell out what the terms are, but we have this positive term here, and then we have the quadratic term here is just the norm squared of theta. So suppose we take a solution to the equation, d star psi equals 0, which we normalize by integration. Then by integrating this, so d star psi equals 0, this is positive, so what you get is that this is less than or equal to 0. And out of that, you can see that, so this term in the middle, of course, has no particular sign, nor does this, but nevertheless, you can estimate this by the sup norm of B, and what you find, and given the fact that this is L2, its norm is 1, what you get is that this thing is bounded by t times something. Well, t times something plus a, but when t is large, it's by t times something. And now, suppose you restrict to an open set in sigma, not to sigma itself, then of course we still get this same inequality because this is positive, so it's less than the integral over the whole of sigma. So now if you choose the open set U to be disjoint from the zeros of theta, then of course you have a lower bound for mod theta squared on this open set, and so you get something like this. And so what this means is that actually as t goes to infinity, this the integral of the norm squared of psi over this fixed open set tends to 0. So what we've got is some localization of solutions to the Dirac equation around what? Around the zeros of this differential theta. Now, now that actually fits very well with the hypercohomology picture, because we know that the hypercohomology, as I mentioned before, this H1, which is another realization of all solutions to this Dirac equation, is isomorphic to the co-kernel of phi here. So it's isomorphic to the set of, if you like, the sections of the co-kernel of phi over these points. Sections of this over these points. So if you like, we can parameterize solutions to the Dirac equation using this hypercohomology by data precisely at these points where the determinant of phi is 0. So now when you, of course, we're now looking at the determinant of phi plus t theta, whereas t goes to infinity. So we can basically carry on this parameterization. We can, as we go to infinity, these solutions to the Dirac equation are, on the one hand, they're concentrating around these points, the zeros of theta. On the other hand, we know that we can actually parameterize the solutions in this hypercohomology situation by that data. So this is providing some information. For example, it's saying that we have some set of solutions which are localized around here, some around here, and then presumably the inner product of these two gets smaller as you go out to infinity, because the inner product is got by integration. So we're getting some information as we go out to infinity about the behavior of the Hermitian structure. It's looking like a direct sum of lower dimensional bundles and which become orthogonal. Of course, it requires more delicate analysis to see exactly what's happening. Now, this is some progress towards actually finding out something about the asymptotic behavior. And the information, which is rather different from Jardin's, so he was just working with a torus. His holomorphic differentials, well, they didn't have any zeros at all, so he had some uniform behavior, L2 behavior about his curvature. Here we have infinity as, well, infinity is, of course, going to be stratified by the multiplicity of the zeros. So even now, there's going to be no simple answer. Maybe there'll be an answer for distinct zeros of the differential, and then when they cluster, when they have multiplicities, there'll be another answer there, and they'll be spliced together in a more complicated way. So I don't expect there to be any really nice answer, but there may be enough to say that we can start relating some of the cohomology groups that appear, sheaf cohomology groups that appear in Bonsdorff's work with L2 cohomology, which is what we would need in order to produce an inverse. Anyway, so finally, I emphasized two special cases. because an answer to either of these will be interesting in its own right. I just want to point out that these actually have an extra feature which may help in understanding the behavior of the transform. So and this is that in any case, if I have a solution to those Higgs bundle equations, A and phi, if I multiply phi by e to the I theta, then that's another solution to the equations. So that gives me an S1 action on the cotangent bundle. It's the usual circle action on the fibers of the cotangent bundle. And in this case, if phi is equal to 0, then obviously this is the Higgs bundle is fixed by this action, and the corresponding transform is going to be invariant under this circle action. Equally, this canonical Higgs bundle, although the Higgs field is not invariant, it actually transforms by a gauge transformation, which preserves the connection. And so, by the same token, what we get is an invariant bundle on the other side. So although the behavior may be quite complicated in general, then in fact, if we throw in this invariance, that might simplify the situation. And there's one final point I want to make about this invariance, and this relates to a theorem of a former student of mine a long time ago, which says that actually if you have any, so first of all, there's a statement about finding a hyperkähler extension of any real analytic Kähler manifold. So if you have a real analytic Kähler manifold, then there's a unique circle invariant hyperkähler metric on a neighborhood of the zero section of the cotangent bundle. Well, here we've got that. That's this flat metric on the cotangent bundle of the Jacobian. The second one says that if you actually have a connection on a bundle over the zero section, whose curvature is of type 1,1, then it extends to a unique hyperholomorphic connection in a neighborhood. So in fact, when you've got an S1 invariant, so we're looking at a hyperholomorphic connection. If for these two Higgs bundles, we would have a S1 invariant connection, and so that will be determined, maybe implicitly, but still determined by the restriction to the zero section. So this would mean, in particular, for the canonical Higgs bundle, that so what we get at the zero section is basically built up out of these Picard bundles based on the sections of k to the 3/2. So this is a degree 3g minus 3 bundle, but as the line bundle varies, basically we're going through all degree 3g minus 3 line bundles. So effectively, if I look at the Picard bundle of that, if I projectivize it, that it's just the symmetric square, or symmetric power, 3g minus 3-dimensional symmetric power of sigma. It's a very canonical object. The point about this is that if I now look at the L2 inner products on these bundles, given by using the hyperbolic metric to do this, then the statement is that actually the hyperholomorphic bundle that we're trying to get is uniquely determined by this the Hermitian structure on this Picard bundle. So that's kind of retracting the injectivity even smaller. But these are avenues where one's trying to get information about something which is very classical, this in particular the hyperbolic metric, by rather devious means. So how successful they'll be, I have no idea. As I say, I'm sure by Blaine's 80th we will be still in a state of ignorance, but in the meantime, let me wish him a happy 70th anyway.
Any questions? At least I have now that Higgs, because it's indeed.
Yeah.
Thank you.